Today, I'm going to discuss Kepler's 3 laws of planetary motion. His first law states that planets orbit the Sun as an ellipse, with the Sun at one focus of the ellipse. An ellipse is more or less an elongated circle. Due to the elongation, we can no longer describe an ellipse with a center point and a radius, as we would a circle. Instead, we now have 2 points, called foci, that define the shape of the ellipse. If we were to pick 2 arbitrary points as our foci, attach a string between them, put a pencil against the string, and try to draw a circle, we would actually form an ellipse. Likewise, we now have 2 axes instead of 1 radius. The larger axis, from the center through the focus and to the stretched part of the ellipse, is the semi-major axis. The smaller axis, from the center to the squashed end of the ellipse, is the semi-minor axis. Note, these axes are from the center to the ellipse. If it went from one end of the ellipse to the other, we would have the major axis and minor axis, respectively. Interestingly, a circle is actually an ellipse. If we bring the 2 foci together so that they overlap, we will now have one focus at the center, and the semi-major and semi-minor axes will now be the same length, which we call the radius. In either case, for our orbit, the planet traces out an ellipse, with the Sun located at a focus. Note, the orbited body is only at one focus. The other focus is just empty space. The second law states that planets sweep out equal areas in equal times. So, if we draw a line from the planetary body to the Sun, that line will sweep out some area in some amount of time. Then, at a different point in the orbit, we let the line sweep out an equivalent area. The time it takes the planet to travel those 2 distances will be equal. We note that to get equal areas, the planet has to travel a longer distance the closer it is to the Sun. This indicates that the planet travels faster the closer it is to the Sun. We can verify this by looking at the conservation of angular momentum. If we define the distance from the planet to the Sun as r, the angular momentum of the planet can be written as L equals 1/2 the mass of the planet, m, times r squared times omega, where omega is how fast the planet is traveling along its orbit, more often referred to as the angular velocity. We note that the areas the planet sweeps out in its orbit form triangles. One side of the triangle is the distance from the planet to the Sun, which we already defined as r. Another side of the triangle is the distance the planet travels in its orbit, called the arc length. We can calculate the arc length using r times the angle swept out by the planet, theta. Since the arc length is perpendicular to r, we can calculate the area of the triangle swept out by the planet as a equals 1/2 r times theta. More accurately, this is written as dA equals 1/2 r times r d theta, where dA and d theta are the infinitesimal area and angle, respectively. However, we will not worry about this distinction here. If we then divide both sides of this equation by t, or dt if we use the calculus form of this equation, we get a divided by t equals 1/2 r squared times theta divided by t. Theta divided by t is the angular velocity, omega. Making this substitution, we see that a divided by t equals 1/2 r squared times omega, which equals angular momentum divided by the mass of the planet. Due to conservation laws, both angular momentum and the mass of the planet are constant. This tells us that a divided by t, which measures the amount of time it takes to sweep out some area, is constant. This thus verifies Kepler's second law of planetary motion. Kepler's third law states that the square of a planet's orbital period is proportional to the cube of the semi-major axis of the orbit. The orbital period is the length of time it takes for a planet to return to the same point in space. The semi-major axis, then, which I defined earlier, is the distance from the center of an ellipse to the stretched out portion on the ellipse. Equivalently, we can reform the law to say that the ratio between the square of a planet's orbit and the cube of its semi-major axis is constant. This means that if we find the ratio for one planet anywhere in the universe, the ratio will be the same for all planets. We can check this with a couple of planets in our solar system. Starting with Earth, the length of our orbital period is, by definition, 1 year. Similarly, the length of our semi-major axis is, also by definition, 1 astronomical unit. If we divide the cube of our semi-major axis by the square of our orbital period, we get a ratio of 1 astronomical unit cubed per year squared. According to NASA, the orbital period for Mars is 1.881 Earth years, while the semi-major axis is 1.524 astronomical units. Squaring the period, we get 3.54 years squared. Cubing the semi-major axis, we get 3.54 cubic astronomical units. Dividing these two, we again find a ratio of 1 astronomical unit cubed per year squared. You can verify this with the other 6 planets in our solar system. In fact, as long as you use the same units, you can check this with any moon, asteroid, or even satellite. The universality of this law was noted by Isaac Newton, who used it to develop his law of gravity. Similarly, while I discussed these laws using a planet orbiting the Sun, all 3 of these laws are universal. They apply to any body orbiting some other body, be it our solar system orbiting the center of our galaxy, or a piece of space debris floating around Earth. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.